classical mechanics, I've been talking about non-inertial reference frames. And the best or the most common example of a non-inertial reference frame is that, which is this, the Earth. So the Earth is a non-inertial reference frame because it's accelerating. And one of the results of that is the tides. So I want to not only explain the tides, but build a Web Python model showing the tidal effect. It's going to be great. So we've got a lot of work to do, so let's just get started. Of course, the number one thing I want to point out is that Earth, Moon, totally not to scale because it's difficult to draw to scale. But we know that there is a gravitational force between these two. So this is the mass of the Earth, ME. This is the mass of the Moon. And this is some distance between them. I'll call that REM. This is the radius between the Earth and the Moon. So the gravitational force, there's a gravitational force on the Moon. And we could calculate that, the magnitude, G, mass of the Earth, mass of the Moon, over REM squared. That's the gravitational force on that. And so why do we have tides? A lot of people would say, well, look, this side of the Earth, there's also a gravitational force from the Moon on the Earth, and this side of the Earth is closer, so it's going to have a stronger gravitational force. That's true. This side is further away, so it's going to have a weaker gravitational force. That's true. Okay. But that doesn't explain the tides. The tides, there's two bulges of water on the Earth like this. There's one on the side of the Moon, there's one on the further side. And so it's funny if you read like introductory earth science textbooks or astronomy textbooks, and it's a complicated enough problem to just say, okay, the tides are caused by the Moon and it pulls on the Earth, and then there's a bulge of water, and there's a bulge on the other side too. Let's go on to the next topic, because it is kind of complicated, right? It's difficult to explain, but we can do it. We can do it because we know what happens with a non-inertial reference frame. How do we deal with a non-inertial reference frame? Okay, so since the Earth pulls on the Moon with that force, the Moon pulls on the Earth with the same magnitude force. So there is a gravitational force pulling this way, and there's a force that way. This gravitational force on the Moon makes it orbit in a circle, right? Just imagine if you took those two and you let it go, they would accelerate towards each other. They'd both accelerate, but the Moon would have a greater acceleration because it has a lower mass. So but that means that the Earth does indeed accelerate too, and it is accelerating because it's also moving in a circle about some point right there. So we don't really care about that motion. We just want to say, yes, it is accelerating. And it accelerates from its center of mass. So we can calculate the acceleration of the Earth because of the Moon, and just by dividing by the mass of the Earth. And it's this way. So how do you deal with a non-inertial frame? How do you make it behave like an inertial frame? Well, what we do is add a fake force. F fake is equal to negative the mass times the acceleration of the frame. So if I calculate the acceleration of the Earth right here, I can, multiply by the mass of stuff. I don't really care. And then I can find the fake force I need to add onto that. The Earth is a rigid object, so the whole thing accelerates. So that means that this point right here has the same acceleration as the center. This point right here has the same acceleration as the center. This point here has the same acceleration as the center. So in fact, what I want to do is, instead of calculating this fake force, I'm going to call it a fake field, a fake gravitational field, because I don't really care about actual forces. So G fake is going to be equal to negative the acceleration of the frame. That's fake, right? That's my fake gravitational force. So everywhere on this Earth, let's just draw a little bit bigger Earth, the Moon's over that way. So I have the acceleration's this way. So I have fake, 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 fake. These are all my fake forces, my fake gravitational fields. But I also have a gravitational field from the Moon, and I need to consider that too. So over here is my Moon, and I can calculate G Moon. I can calculate, and over here, the G Moon is greater than a fake. So this is a little bit bigger. And we'll show this. Over here, the acceleration, the field of the Moon is smaller than the force. the fake field. So the net force is that way. So that shows you those two tides right there. So let's just do this. Let's make the Earth. Let's show all these vectors, and then we can plot these vectors, these net vector, G fake plus G moon over the whole Earth. It's going to make a great visualization. Okay, so first I do need to say one thing. Okay, let's say this is the location. I'm going to call that RM. It's the vector location of the moon. Now suppose I have some location right here. I'm going to have my Earth at the origin. So I have some location right here, R0. That's my observation location. I'll call it RO. And I know this is RM. That's RO. I need this vector right here. This is going to be RO minus RM. And I can call that R. So I can use that to calculate the gravitational field. So G moon, this is constant. We're going to have to calculate that too. But G moon is going to be negative, it's going to be this way, right? Negative G mass of the moon over R squared R hat. So R hat's a unit vector in this direction, so I can calculate without wherever I need to go. And now we're going to need to draw these arrows. We're going to need to scale that. We have a lot of artwork to do. So let's get to work with the artwork. Switching over to WebVPython, you know I'm going to give you the code because that's what I do. But you know I like to make the code too, so it's going to be fun. Okay, so here we are. I've already put in the constants that I forget. So here I have the gravitational constant. I knew that one. I have the radius of the Earth. I'm going to need that. I have the location of the moon. So I put it in the positive x direction. And then I have the mass of the Earth and the mass of the moon. I actually don't need the mass of the Earth, but that's fine. So let's just draw the Earth. I'm not going to draw the moon. It's going to mess everything up. So Earth is equal to sphere. The position is vector 0, 0, 0. Yes, I didn't tell you this. It's WebVPython. So this has these objects like a sphere that we can draw, and we can make awesome things with them. The radius of the sphere is RE. And then I'm going to give it a texture. Texture equals textures dot earth. Run. Check that out. Isn't that nice? Pretty cool. Okay, I do want to do something. I want to just add onto this. Let's put a comma and return. Shininess, shiny, I think this is how you spell it. Shininess equals 0. I like it better. So the default texture is like a glass sphere, and there is a light source somewhere. But if you turn off the shininess, I just think it looks more appropriate in this case. I like that. Nice. Okay, and I didn't even really make anything. I didn't do any art. I just made that. Okay, the first thing I want to do is to calculate G fake, the fake gravitational field. We just need to do that once. GF is going to be equal to, so I have my thing in the, I've already said it's in the positive x direction, just like in my picture over here. So the gravitational force is going to be in the negative x direction. So let's just do this. It's going to be negative G times the mass of the moon times the mass of the Earth, divided by the mass of the Earth, times norm Rm divided by mag Rm squared. And let's print that. I'm going to put GF equals GF. I'm going to leave off the units. Okay, so my moon's in the positive x direction, so the gravitation, the fake force should be in the negative direction. That seems like it's right. Okay, and that's at the center, and that's going to be true everywhere around here. Let's just go ahead and draw an arrow for that at the location I want to do right here on the positive side right there. So I'm just going to go ahead and do that. Let's just draw that. RO equals vector RE0, 0, right? So that's on the x-axis, the radius of the Earth. Now I can calculate R, just like I said before, up here. R is going to be equal to RO minus RM. And now I can calculate the GM for that. So GM is going to be negative G times the mass of the moon times norm R. Norm is a unit vector in the direction of R, divided by the mag. Mag is the magnitude of the vector R. It's built into Python. And let's just print that. Okay, so there's my gravitational field in the negative x direction. That's my fake gravitational field. This is my actual gravitational field in that direction. And you'll notice that if you just compare those two numbers, then GM is greater than GF. So the net field, including the fake, would be to the right, which is what we want, right? It should be that direction. Let's just go ahead and draw arrows for these two things. Okay, so now I'm going to just draw them and then I'll show you, I'll fix it. Because it's good to learn that way. Now, I'm not even going to name the arrow because I don't really care about the arrow. So let's just make an arrow for GF. Arrow, and I'm not, see, I don't have to say something equal to it. Just say arrow. It will make an arrow. The position is going to be RO, not R0, RO. The axis is going to be equal to, and you may see the problem here. This is going to be the arrow for the fake gravitational GF. So arrow is GF, that's a vector, and let's make this color equals color dot cyan. And it's going to run it. And maybe you know what's going to happen. And don't spoil it for everyone. And there you go. And the problem is, like, that's the Earth. It's, you know, 1,000,000 meters in radius, and that's 10 to the negative fifth long for the thing. So it's not big enough. Let's make a scale vector up here. I'm going to call it scale, and let's say it's 1 times 10 to the 10th. I'm just picking something. I think that will work. So I'm going to multiply this by the scale. So that will make the arrow longer because I'm plotting a gravitational field, but I want it in meters. I want it to see, I want to be able to see it. So let's see if we can see this. And you can't see it because even if it was there, because it's inside the Earth. So let's make the Earth, give it some opacity, so see-through. So opacity equals 0.4, and now I'm going to run it again. And you still can't see it. Oh, there it is. It's super tiny. Let's make it a little bit, let's do this 10 to the 11th. Okay, there's my arrow. That's the fake gravitation, the acceleration vector. Good. Okay, now let's make an arrow for the other one. I'll make it magenta colored. Arrow POS equals RO. RO axis equals scale times GM. Color equals color dot magenta. Magenta. Sometimes you just can't spell, and you got to sound it out, and that's fine. Okay, so there are my two arrows right there. It's difficult to see that one's bigger, but it should be the magenta arrow is bigger. Let's just go ahead and do it on the other side of the Earth just to see if they look fine. So down here, I'm just going to copy all this stuff, right? Because I'm just going to redo the exact same thing. And I'm just going to change this to negative. And then it should work, right? It didn't give it names or anything, so it should be fine. And there you go. So in this over here, the fake field is greater than the gravitational field. Over here, the gravitational field is better. This should make the two bumps. Okay, now let's go ahead and replace this with just the net arrow, the net field. I'm going to make that. So I'm going to get rid of these two arrows right here. I'm going to get rid of this one. And I'm going to make one that's the sum of those. So arrow, POS equals RO, axis equals scale, times. Now I need to add those two things together. So GM plus GF. And then let's make this yellow. Color equals color dot yellow. And then do the same thing down here. Get rid of that one. I'm going to keep this one and just say GM plus GF and color equals color dot yellow. So, because it got to be a different color, it's a different thing, right? And there you go. So you can't really see it. See, there's one, and there's the other one. They're too small. So I need a larger scale. Let's just increase that by a factor of 10. Okay, that looks pretty good. Okay, both pointing away. So now we've done it. We're finished, except we want to make it prettier. So what I want to do now is to kind of like go all the way around the Earth, and I want to plot out a bunch of arrows. So I'm actually going to do this two ways. So just hold on to your horses. We're making art. Art takes time, so we're going to do our art stuff. Okay, so what I want to do is I'm going to break this into, let's say, 20 spots all around the Earth. And it's going to go in the XY plane for now. Okay, so this stuff, let's just get rid of Earth. GF is fine. RO. Let's just get rid of all this stuff. I'm just going to comment it out. So you can, in WebVPython, you can comment with 3 quote like that, and that's all commented out now. It's still there. It didn't go away. Okay, theta equals 0. D theta equals 2 times pi divided by 20. So if I break this into angles, I can move angularly around that Earth and plot my points. So to do that, I'll just say while theta is less than 2 times pi. And then for each angle theta, I can calculate my RO. So RO is going to be radius of the Earth times the vector cosine theta, sine theta, 0. So then I can just change my theta and I just redo it. I'm just going to do the same thing over and over again. So the next step is to make R. R is RO minus Rm. Now I can calculate Gm. Gm is negative G times mass of the moon times norm. Just the same as before. Norm R divided by mag R squared. And now I can make my arrow. I'm not going to give it a name. I'm just going to make it. Arrow position equals RO. Axis equals scale times GM plus GF. And then I do want to make it yellow. If you want to make yours a different color, you make yours a different color. This is your thing too, right? Now, before I run this, I need to do something very important. I need to increase my theta angle. Theta is theta plus d theta. Otherwise, it would just never go anywhere. Let's see if this runs. If it does, you know, I could have made a mistake. And I didn't. Check that out. Look at that. And so that's not the tide, right? That's a visualization of the tide. But you'll notice up here that the net gravitational field pushes in, and you get this nice tidal effect. Good enough for a textbook or whatever you want. That's pretty nice. But we can make it better. What if I want it all over the Earth in 3D? So you could do some type of, you know, how do you like evenly spread things around the Earth? That's not completely trivial. I can't just break it into thetas because as I move other ways, then I'm going to have to, you know, do something different. And so when I'm dealing with spherical coordinates, I don't want to make them completely even. Instead, I want to cheat. So I'm going to cheat by doing this with a Monte Carlo distribution. And so what I'm going to do is just randomly distribute them over the surface. And again, there's more than one way to do this, but I'm just going to show you the way I like to do it. Okay. So I'm going to let's just say n equals 0, n equals 500. So I want to make 500 different points. And so what I'm going to do is randomly generate a value between negative RE and plus RE, and then if it's in this thin shell, of the surface of the Earth, then I'll plot a vector, and if not, I'll just throw it away and start all over. That's what we're going to do. Okay, so we do need a DR. How thick do we want our shell? And you could do whatever you want. I find 500 works for that too. Okay, so I'm going to run this as long as n is less than 500. So I'll get 500 pieces. Now, the first thing I need to do is to make this temporary vector. So RT, it's going to be a vector. And so the x-coordinate is going to be from negative RE to RE. So I can do that by saying RE times 2 times random. So random gives you a number between 1 and 0. So this gives me a number between 0 and 2. And then I subtract off 1. I get a number between negative 1 and 1. I multiply it by RE, and that's what I want. Now I want that exact same thing in the x, y, and z direction. So I'm going to copy that. X, y, z. So now I have a temporary vector. But I don't know if I want to keep it. So let's just say if. Okay, so I can find the distance from the origin. So if the magnitude of RT is less than, see, it's not going to be equal to the radius of the Earth, right? So I want it to be less than the radius of the Earth plus dr, and mag RT is greater than RE minus dr. So there I have my little window of radiuses that I want it to fit in. And if that's true, then I'm going to keep it. So if I keep it, I'm going to then calculate RO. RO is just going to be RT. And then this is the same, that's the same, that's the same. I'm not going to have theta, but I do want to increase my value of n. N equals n plus 1. So I'm only going to count it if I plot it. Does that make sense? Okay, I think this should work. I haven't saved in a while. I should probably save because there's a very good chance I made a big mistake because I make mistakes. Okay, let's see if this works. Run it. No, it did not work. Can't find dr. I said dr. dr, aha. I called it dr, not dr. Okay, so down here, I just need to change if. This is dr, not dr. And this is dr. And that's the only thing that I had to do to fix it. I'd be amazed. Oh, it's, ha ha. Check that out. I mean, that's just cool, right? And if you want to play around with the opacity and the shininess and the size of the arrows and the number of the arrows, you can do all that stuff. But there's your visualization of the tides. And that's where you can see you have a bulge on that side, you have a bulge on that side. You do not have a bulge up here, you do not have a bulge down there. And that's that. That's the end. And I'm going to give you the code because you know I like to give you the code. So save that. You're going to get the code. Hope you enjoyed that. That was fun. I had a great time. It's not just physics, it's art. Talk to you later.